You are looking at a computer that runs on living human brain cells, a cluster of lab-grown tissue physically wired into a silicon grid. Inside a facility called Cortical labs, researchers have built a series of these biological setups. They call the early version dish brain, and their newer model is designated CL1. These living cells actively receive input and execute commands. The researchers successfully trained this biological tissue to play Pong, and more recently to navigate a level in the video game Doom. The biological processing unit inside the Doom machine is made up of roughly 200,000 human neurons. Those specific cells take in data, they make decisions, and control the in-game movement. By substituting rigid silicon processors with living human tissue, these machines no longer just mimic biological logic, they run on it. A piece of a person is now serving as the physical substrate for digital software. To build these systems, scientists don't have to extract cells from an actual brain. A breakthrough by researcher Shinya Yamanaka proved that you can take regular adult human skin cells, reset them, and grow them into completely new neurons. A typical lab-grown brain organoid forms a three-dimensional sphere, but to talk to a chip, it must be forcefully flattened into a two-dimensional layer across an electrode grid. This grid acts as a translator, converting digital game code into electrical signals the biology processes. By forcing living tissue to conform to the exact physical dimensions of a microchip, the design strips away the tissue's natural shape, turning a living organism into an interchangeable hardware part. Building computers out of human cells is driven by a very practical problem. The artificial intelligence industry is running out of electricity. Companies like Meta are pouring billions into massive new infrastructure just to handle the power load. The compute power required to train new AI models doubles roughly every 6 months. That demand is outstripping our physical ability to construct new power plants and support sprawling data center complexes. The shortage is severe enough that tech giants are now signing long-term deals to lock up huge chunks of the grid years in advance, and even paying to restart old decommissioned nuclear power plants to guarantee their supply. This chart shows the massive exponential energy consumption of AI data centers compared against the flat 20-watt requirement of human biology. Your brain, which handles complex logic effortlessly, runs on almost zero electricity. We are using entire power plants to mimic a fraction of what living tissue does naturally. A Swiss company called FinalSpark is already commercializing this biological efficiency. They keep clusters of human mini-brains alive in a lab and rent out access to them over the internet, allowing researchers to run operations on a platform that uses up to 1 million times less power than standard chips. The cost of intelligence is no longer just a software problem. As the search for massive energy supplies dictates the pace of AI growth, the extreme efficiency of biology has shifted from a scientific curiosity to a viable commercial alternative. Curious, but this introduces a mechanical problem. You cannot offer a cluster of cells a treat or give it verbal instructions. So how do scientists actually force a blob of tissue to learn a digital task? The solution relies on a concept called the free energy principle. At their core, living biological neurons hate unpredictable chaos. Their most basic instinct is to keep their environment stable and avoid surprise. When the cells miss the ball in Pong or take damage in Doom, the computer floods them with scrambled, random electrical noise, inducing a state of deep biological stress. The inverse is also true. When the cells successfully hit the ball back or avoid taking damage, the chaotic signal is immediately replaced by a calm, steady, predictable rhythm. These cells have no concept of Pong or Doom. They aren't executing strategy or trying to win a match. Their only motivation is a desperate biological drive to make the tortuous electrical chaos stop. A skeptic might point out that in these setups, a standard computer chip still watches the screen and handles the heavy lifting of the game logic. The living cells only play a small reactive part. But high-level logic isn't the primary concern. Neuroscientist Mark Solms proposes a theory that challenges our basic understanding of what is required to feel. Solms argues that the capacity to feel does not sit at the very top of complex human intelligence. Instead, feeling evolved first. It exists at the very bottom of basic biological survival, moving toward what keeps a cell alive and recoiling from what damages it. This connects directly back to how the biocomputer is trained. That instinctual drive to avoid chaotic electrical noise and seek a calm state might be the exact biological origin point where feeling begins. Instead of building a silicon machine and waiting for it to eventually wake up, wiring human tissue into a forced feedback loop might trigger the physical mechanics of suffering at the absolute lowest cellular level. If these engineered cells are actually experiencing some primitive form of suffering, science currently has no definitive way to measure or prove it. In 2006, a scientist named Adrienne Owens studied a young woman who had been completely unresponsive. She was diagnosed as vegetative, and her doctors assumed she felt absolutely nothing. When Owen placed her in a scanner and asked her to imagine playing a sport, her brain lit up. The test proved she was entirely conscious and awake. She simply lacked the physical ability to show it to the outside world. If we can miss a fully aware human being lying right in front of us, spotting awareness in a clump of isolated tissue is impossible. From the outside, a network of cells simply responding to bad electrical signals looks completely identical to a network of cells recoiling in silent pain. In the push for energy efficiency, we are engineering systems that rely on a drive to avoid chaos, the same drive that underpins our own sense of feeling. We have built a machine that we cannot distinguish from something that suffers.